In this video, we're going to have a look at static equilibrium and moments. When we considered terminal velocity and objects falling under gravity, we considered two forces: weight, which we said acted from the centre of mass of an object, and air resistance, that drag force, which also acts at the centre of mass of an object. However, there are plenty of examples where forces act from a lot of different points. And in fact, we might have a lot of different forces, all acting in different directions from different points on an object. And so working out what happens requires us to need to know something about moments. A good example of the moment in the human body is the arm joint at the elbow. The elbow is acting a little bit like a pivot, it's like a hinge. And when you try and lift something up, the weight of what you're trying to lift up is trying to turn your arm in a certain direction. And so that muscle has to work in the opposite direction to try and turn your arm back again. And that is essentially what a moment is all about. It's the turning effect of a force. The idea that forces don't just get things to move in a straight line, but they can sometimes get objects to turn as well. So the question is, what things are going to be important for us to consider? And it's three things. Number one, the size of the force. Number two, the direction that the force acts in. And thirdly, where the force acts. So the example that you've got in front of you, changing a tyre, I remember doing this the first time I had a flat tyre, and the wrench that was in my car was the tiniest wrench I'd ever seen. Absolutely no way that was going to shift the bolt and turn the bolt to take the wheel off my car. So I had to phone the breakdown company. They came along, they tried my wrench, also unable to take the bolt off the car, which I guess made me feel a little bit better. He then went back to his van and got a wrench which was like 3-4 times longer, and with a little bit of effort managed to turn that bolt, take the wheel off my car so that I could change it. And that's a really good example of where it isn't just about the size of the force that I can apply to the wrench that's important. It's also where that force acts and how I hold my hands to direct that force. All three things are important, and that's what we're going to have a little look at. Firstly, though, let's define what we mean by a moment. A moment is the turning effect of a force about a pivot, and a pivot is always a fixed point on an object. We can calculate the size of the moment using the equation moment equals force times distance. Now we need to define what we mean by distance. And in the orange box, we're going to define it as the perpendicular distance between the line of action of the force and the pivot. Now that's a really hard sentence to try and understand what that actually means, and so we're going to unpack that in a few moments. But first of all, let's just look at units. The unit of a moment is the Newton meter. Now that makes complete sense, doesn't it? Because it's force times some kind of distance. So dimensionally, the unit of the moment is the Newton meter. But I'd like to show you that that's actually equivalent to the joule, and that's going to really help us to understand what a moment is all about. So let's have a little look then at converting both of these into SI units. So to do that, I'm going to use Newton's second law because F is ma. So the Newton is equivalent to mass is kilograms and acceleration is meters per second to the -2. So therefore the Newton meter is what we've just written on the line before multiplied by meters. In other words, it's kilograms meters squared, because I've multiplied by meters, seconds to the -2. So the joule I'm going to define using one of my equations of energy. Remember, I can use any equation and it will still work and give you the same outcome. So the joule is equivalent to kilograms for mass, meters per second squared for G, and meters for H. In other words, just to combine and simplify, it's kilogram meters squared seconds to the -2. The joule is equivalent to the Newton meter, which is the unit of the moment. So one way that we think about moments then is the amount of work that a force can do to turn an object. The amount of work a force can do to turn an object. And it's pretty obvious, isn't it, looking at that equation, that one way that I can increase the turning effect is to apply a bigger force. But what if I can't? What if the strength of my arm is fixed and I can't apply a bigger force? Well, the other thing that I can do then is to maximize the distance between where I apply the force. So in this example on the PowerPoint, it's there, and where the pivot is. Okay, that is the distance, isn't it, between where the pivot is, which is down here, and where I apply the force, which is at that point there. However, the direction that the force acts in is also important. Okay, you've got 3 diagrams in front of you, and I would guess that your gut instinct is telling you that the most effective direction to apply that force from is in the first diagram. And you'll notice that there's a right angle between the wrench and the force. I think your gut instinct will also tell you that is the wrong way to try and loosen that bolt. Okay, applying a force parallel along the length of that wrench is going to have no effect at all. So let's have a little look then at what this direction bit is all about. And I'm going to return to our definition of x. It's the perpendicular distance between the line of action of the force and the pivot. And I think we need to spend a few moments explaining what that actually means. So let me recreate the diagram on the right, where you've got a pivot, a triangular pivot, and you've got some kind of force from that weight that we've put on top of that beam. Okay? What is the line of action of the force? It basically means the direction that the force is acting in. So if I just overdraw the force vector, that is the line of action of the force, because the force is pointing vertically downwards. What I'm now going to do is to draw a second vertical line from the pivot so that it's parallel to the line of action of the force, and I'm going to use that to define my distance. That is what perpendicular distance between the line of action of the force and the pivot means. In the diagram that you've got on the left, we've got the center of mass of the object somewhere near the center of the object. That's the pivot. And we are being shown that we've got a force vector acting on one side of the object. That is the line of action of that force. And so what I'm going to do again is to draw a line parallel to it through the pivot, and I'm going to define x as the perpendicular distance between the line of action of force and the pivot. You can see there is my right angle. Okay. What if we've got something even more complicated than that? So we've got our beam, and this time we've got the pivot at that end of the beam. And just be careful that you've identified where the pivot is. Now, the center of mass of the beam is the center of the object. And so the weight of that object is acting from the center of the beam vertically downwards. So working out the distance between the perpendicular distance of the line of action of the force and the pivot is quite easy here. Okay, so I draw my little dotted line, also vertically down from the pivot, and that would be the distance that I would be calling x. However, on the left-hand side, we've got some kind of force, and this force is acting at some angle to the vertical, some angle theta. So your strategy is to resolve vector f and to find out the vertical component of it. And the reason that you're going to work out the vertical component of it is because weight, which is the other force, is also acting vertically. So I'm going to draw in green this time. That is the line of action of that force. So I need to know how big that force is. And it looks like it's the adjacent of a triangle. So it is F cos theta. That is the vertical component of the red force vector. And that's the component that I'm interested in. So I now draw my dotted line from the pivot. And there's the line of action. And that's the distance that's important. That is the perpendicular distance between the line of action of the force and the pivot. So if we now return back to the diagrams that I showed you a few moments ago, now you should be able to see why the top diagram is going to provide the biggest turning force. There is the line of action of that force, and I've drawn my dotted line parallel from the pivot, and you can see the distance between those two. If we then compare it to the second diagram, there is the line of action of the force, there is my dotted line from the pivot, and you'll notice that that distance is now less than the distance in the first diagram. Remember what a moment is. A moment is the force that you apply, and we'll assume it's the same in both diagrams, multiplied by the perpendicular distance between the line of action of the force and the pivot. And that distance is smaller in the second diagram. So therefore the turning effect is going to be smaller. So in other words, if you want to maximize the turning effect, apply that force at right angles to the wrench and not at some angle. And obviously, applying at that angle would provide no moment at all, okay? Because you cannot draw a perpendicular distance between the force and the pivot because the force is acting parallel to the wrench. Okay, so to conclude this first section, a moment is the turning effect of a force. It is calculated using the equation force times x, where x is the perpendicular distance between the line of action of the force and the pivot. And three things are important: the size of the force, where the force acts, and the distance away it is from the pivot are all important. Okay, let's have a little look at some examples. Here's your classic example then of moments. So we've got a crane, and what we don't want it to do is to topple over. We want it to be able to pick up a load of objects and move them from place to place, and we want the whole thing to remain upright without falling over. On that diagram, you've got four forces. You've got the weight of the counterbalance. Okay, the counterbalance are those weights that we kind of bolt to the far end, the back end of the crane. We've got the weight of the tower, we've got the weight of the object that we're trying to pick up, and then we've got the weight of the crane itself. Okay, the jib is the horizontal beam, which is part of the crane itself. Okay, now I'm going to argue that only three of those are going to provide turning effects. I think the counterbalance does. I think it's trying to turn the crane that way. And the reason I think that is because you can see on the diagram, and I'm now going to highlight it in a color that perhaps you can see. There we go. There is the pivot. Okay, that is the point at which that crane is going to rotate and turn. So the counterbalance is going to try and turn that crane in that direction. The weight of the object, though, I think is going to try and turn the crane in that direction, as is the weight of the jib. But I don't think the weight of the tower itself is going to turn the crane at all. And the reason I think that is because the weight of the object acts down vertically through the central column of that crane, and it's in line with the pivot. Okay, so it is not going to create a turning effect. So 3 out of those 4 are providing moments. So how do we describe a moment? Up, down, left and right doesn't really work for us, so we're going to use the language of clockwise and anti-clockwise. So that is providing a clockwise turning effect, a clockwise moment. But these 2 forces are providing anti-clockwise moments. So we've got 1 clockwise moment and 2 anti-clockwise moments. So how do we know that that crane is not going to topple over? We need to apply what we call the principle of moments. And the principle of moments says this: if you sum up, and that's what that sigma symbol means. Sigma means to sum up, to add up. If you add up all of the clockwise moments and you add up all of the anti-clockwise moments, you should find that they are equal. And that is how an object remains in what we call static equilibrium. Static equilibrium means it's not rotating to the right and it's not rotating to the left. It's static. And so another way of saying that then is overall there is 0 resultant moment acting on that object. So let's have a little look at how we do some calculations based upon that then. Okay, so let's redraw my crane. So there's the crane structure, okay, and we've got a force which is the load that we're trying to pick up, okay, that bit of pipe or something, force number 3. We've got this force here, F2. Now, it's not obvious what that is, but it's where it is that's going to help us to work that out. I think it's about halfway from the pivot to the end of the crane. Okay, and that's the clue then that is the center of mass of that part of the crane. So it's got some kind of weight to it. We're going to call that F2. So the perpendicular distance between that force and the pivot is D2, and similarly D3 for force number 3. On the back, we have to put some counterbalances, okay? Otherwise, the crane is going to topple over. And we're going to call that force number 1, and it's a distance D1 from the pivot. So I'm going to apply my principle of moments. The sum of the clockwise moments is equal to the sum of the anti-clockwise moments, okay? And I'm just using CM and ACM as shorthand. Please don't do that in the exam, but just for note-taking, that just helps us, doesn't it? Okay, so what's clockwise, what's anti-clockwise? I think F3 is clockwise, I think F2 is clockwise, and I think F1 is anti-clockwise. So I've got 2 clockwise forces. I've got F2 at some distance D2, and I've also got F3 some distance D3. And if I add up those 2 moments, that's equal the 1 anti-clockwise moment, which is F1 D1. And as long as that condition is kept, that crane will not topple over. So let's have a little look at some actual numbers, calculation then. Okay, the classic seesaw question. So we've got our pivot and you've got some dimensions and some weights. So we've got big guy over here, little guy over here, and that seesaw is in equilibrium. So even though we've got 2 very unequal forces acting either side of the pivot, the point is they're really different distances away. So the big guy is 3 meters away and the little guy is 35 meters away. If that seesaw is in equilibrium, then the sum of the clockwise moments and the sum of the anti-clockwise moments must be equal to each other. Okay, the big guy producing the clockwise moment. the little guy producing the anti-clockwise moment. And they're going to be equal to each other. So the big guy's got a force, which is his weight or her weight of 1,000 newtons, 3 meters away. And the little guy has got a force that we don't know what that is, but he or she is 35 meters away. So we can solve that quite easily then, and we can figure out that as long as that little guy has a weight of 85.7 newtons, then that seesaw is going to be in equilibrium. Okay. Now you've got something in addition on the PowerPoint slide down here. Let's just kind of talk about that then for a moment. This is talking about the reaction force. So you've got two people on a seesaw pushing down on the earth, and the earth must be pushing back. So we know that the big guy has a force of 1,000 newtons, and we've worked out that the little guy has a force or a weight of 85.7 newtons. So add those two forces up, then we've got a downward force of 1,085.7 newtons. And so therefore the ground must be providing an equal and opposite reaction force, mustn't it? Okay, the seesaw isn't sinking through the ground, it's not floating in the air, so therefore the downward weight is equal to the upward force at that reaction force. So I know that's taking us a little bit away from moments, but we're going to look at that idea of reaction force in just a moment. Okay, beware the person lifting question. This often catches people out. But once you've clocked into it, hopefully you won't be caught out by it. So we've got a beam, we've got some kind of weight here, and we've got some kind of weight here. And let's just imagine for a moment that these two are not in equilibrium. Okay, let's imagine that one of the moments is bigger than the other. So let's kind of put some numbers in to illustrate this then. Let's imagine that's 3 meters from the pivot, that's 4 meters away from the pivot, and then we've got an extra 1 meter from the weight to the edge of that beam. We've got a 100 Newton force here, and we've got a 120 Newton force here. Okay, right, let's have a little look at the two moments then. So let's look at the clockwise moment and anti-clockwise moment. That is providing the clockwise moment, and that is providing the anti-clockwise moment. So clockwise, we've got 120 newtons, and it's 4 meters, isn't it, away from the pivot. And anti-clockwise, we've got 100 newtons, and that's 3 meters away from the pivot. Now you can instantly see those two are not equal to each other. Okay, in other words, that is not going to be in equilibrium. 120 times 4 is 480, so we've got a 480 Newton meter clockwise moment, but we've only got a 300 Newton meter anti-clockwise moment. Not equal. That seesaw is going to tip. Okay, it's going to rotate. What direction is it going to rotate? It's going to rotate in the direction of the biggest moment. It's going to rotate clockwise. So what's the solution? The solution then is to have somebody standing here holding on to the end of that beam, and they've got to provide the missing bit of moment. And the missing bit of moment has to be anti-clockwise. So we need this person to lift the beam upwards, not push it down again. So the person has got to provide an anti-clockwise moment. How big does that anti-clockwise moment need to be? It needs to be the missing bit. So the person must supply a 180 Newton meter anti-clockwise moment. 180 Newton meters because that's the difference between 480 and 300. anti-clockwise moment because that's the smaller of the two moments. So what force then has that person got to supply? So their moment is force times perpendicular distance from the pivot. We know that that moment has got to be 180 Newton meters. We don't know what the force is. The distance from the pivot, now this is where again we've got to be careful, is 4 and 1 meters away from the pivot. In other words, 5 meters away from the pivot. And that means that the person has to supply a 36 Newton 36 Newton force. So a 36 Newton force applied 5 meters from the pivot will provide that 180 Newton meter anti-clockwise moment that we need to keep that in equilibrium. Next up, let's have a look at reaction forces. So you've got the Golden Gate suspension bridge. So there it is, being held up by 2 pillars. You've got cars, you've got people, you've got all sorts of extra kind of weight acting on the bridge. And I guess you've also got, acting from the center of mass, you've got the weight of the bridge itself. And that's going to provide a downward force on each of the 2 piers which are holding the bridge up. So you've got a force over here, you've got a force over there, and in response, the ground is providing an equal and opposite reaction force and an equal and opposite reaction force there. If it doesn't, the bridge is going to sink into the ground. So what engineers have to do then is they have to think about all the forces that might act on that bridge and make sure that the 2 piers can provide enough, well, not the 2 piers, they need to make sure that the 2 pieces of ground that the piers are sitting on can provide enough of a reaction force to stop that bridge from sinking. And they have to kind of consider, well, what would happen if we had like loads of cars all over here and none of them at the other end of the bridge? We're going to expect all these cars to provide a big clockwise moment there, and that's going to really affect the forces acting on the 2 piers. So let's kind of have a look at that kind of idea, but perhaps a slightly more simplistic example then. Okay, there's your diagram. And this time we've got 2 pivots. And that's the big difference now between this question and all the questions that we've looked at so far. In the same way that the bridge has got 2 piers sunk into the ground, we've got 2 pivots, and we're now going to have a little look at what goes on. Okay, I'm going to recreate that diagram for us then. So there's the beam. Okay, there's your pivot 1 and there's your pivot 2. And we're told a number of bits of data. So the first bit of data we're told is that there is a 9810 Newton force acting from what it looks like the center of the beam. That must be the weight of the beam. Okay, and it is acting at the center of mass of that beam, which means that it is 2 meters from that pivot and it is 2 meters from that pivot. Okay, we've then got an extra 1 meter of distance over there, and then on the left hand side we've got some object providing some force of 785 newtons, and that object is half a meter, and we've got an extra half a meter over there. Okay, so we've got 2 weights acting downwards. Okay, and we've got 2 reaction forces acting upwards. So we've got the reaction force at this point, R1, and we've got the reaction force at that point, R2. So in other words, the beam and the weight on the beam are kind of pushing down, and the ground in response is pushing back up again with 2 reaction forces. Now, what would be nice to know then is how big are those 2 reaction forces? And I think you can probably see that they're not going to be the same, because although the beam's centre of mass is the centre of the beam, on the left-hand side, we've got that extra object, and I think you're going to expect R1 to need to be bigger than R2. So the question is, how do we go about doing this? We split this up into two separate calculations, and we do something which we call taking moments about. And we're going to take moments about R1, which basically means let's just think about what's happening here at R1 and ignore what's happening at R2 for a moment. Okay? So at R1, the sum of the clockwise moments and the sum of the anti-clockwise moments are equal if that beam is in equilibrium. Okay, the clockwise moment, I think, is being provided by the weight of the beam, 9,180, and it's 2 meters away from that first pivot. The anti-clockwise moment, I think, is provided by that 785 Newton weight, and it is 0.5 meter away from the pivot. However, we've also got pivot number 2 pushing upwards, and I think pivot number 2 is providing an anti-clockwise moment. Okay, the beam is pushing down on pivot 2, and in response, pivot 2 is pushing upwards, and it's providing that anti-clockwise moment. So we've got the force from R2, which we'll call R2, and it is 4 meters away, isn't it, from the first pivot. Okay, you solve all of that, and you can work this out for yourself. R1, sorry, let's just actually write something that makes sense. R1, no, I was right the first time. R2, here we go, is 4,807 newtons. Okay, so by taking the moments about the first pivot, we actually get to work out the reaction force at the second pivot. So what we're now going to do is do the same again, and this time from the perspective of R2. So from the perspective of R2, what are the clockwise and the anti-clockwise moments? The clockwise moment, I think, is provided by R1. Okay, the weight of the beam is pushing down on the first pivot, and the first pivot in response is providing a clockwise moment. Okay, so that is R1 multiplied by 4 meters. It's 4 meters away from that second pivot. Right, what are the anti-clockwise moments then? I think they are the 9,810 force, and that is 2 meters away, isn't it, from the second pivot? And also we've got that 785 Newton force, and it is 2.5, so it's actually 4.5 meters away from pivot number 2. And if you solve all of that, you calculate R1 to be 5,788 newtons. Okay, so what have we done? We've considered everything from the perspective of that first pivot. And that's enabled us to work out R2. We've then considered everything from R2, and that's enabled us to get R1. Okay, now how do we know that these two numbers are correct? And the answer is we add them up. And if you add up 4,807 to 5,788, you get 10595 newtons. Okay, what is that? that is R1 and R2. That is the total reaction force. If that seesaw is not sinking into the ground, then the weight acting downwards must be equal to the reaction force acting upwards. So we do a little test and we kind of go, let's add up the weights acting downwards. So let's add up F1 and F2. 785, that's F1. 9810, that's F2. 10595 newtons. Total reaction force and total weight are the same value, and they should be. Okay, so we've used the principle of moments to work out R2 and R1, and then we've done a double check to see whether they're correct or not by comparing the total weight and the total reaction force. So in summary then, this is what it looks like. If an object is in static equilibrium, then there should be no resultant moment. So the clockwise moment and the anti-clockwise moment should be equal to each other, i.e. they add up to 0 because they're in the opposite direction. And the resultant of all the forces should be equal to 0. In other words, the downward weight and the upward reaction force values have equal and opposite magnitude and direction. So they add up to 0 as well. Okay. Before we finish, let's have a little look at some kind of typical exam questions then. So if we begin with this one, this is one of your kind of more straightforward questions. The thing to just be careful about is defining that distance from the pivot. So the object, the moon on the left, the distance is x. For the object on the right, we don't know it. So you have to express that distance in terms of what you do know. Okay, and this distance here is the total distance, 0.50 minus x. Okay, and that's as well as we can define what that distance is at this point. Okay, so have a look at the mark scheme. Have a look at how they've applied the principle of moments, and you will notice that 0.5 minus x term appearing there. That is the distance between the star, the line of action of the star, and the pivot, which is at A. Second example of the question, forces acting at angles. Now, it's really easy to get this wrong. The weight is acting vertically downwards. So we need to look at the vertical component of that force. Okay, so that looks like the adjacent of the triangle. So cosine. So you've got t cos 40 acting vertically. Okay, and that's what you notice in the mark scheme. Now, the reason I said to be careful is examiners sometimes throw in that angle. All right, and it's just making sure that you've got the right angle identified. Thirdly and finally, here is your two pivot kind of question. Okay, so that would be really good for you to have a go at one of these as well. The thing to notice in here, though, is, and this is the other way that examiners sometimes throw us, they haven't given you weight or force. They're giving you mass. So you would expect to be multiplying that by 9.81 to turn it into force, and you'd be expected to do likewise with that. Okay. So to conclude, we know that a moment is the turning effect of a force. We know that the size of the force is important, how far it is from the pivot is important, and the direction that it acts in is important. We know that the principle of moments is what we use to predict static equilibrium. And if an object is not turning, then you can be confident that the clockwise and the anti-clockwise moments are equal to each other. And we've also had a little look at what happens on the two pivot examples, where you've got an object providing a downward force and the ground providing that equal and opposite reaction force. And the summary from that was that in static equilibrium, the resultant moment is zero and the resultant force is zero. I've then gone through some tips and strategies for those typical exam questions. And the next best thing for you now to do is to practice through a series of examples for yourself.